Everything in our universe has an invisible mirror twin. If these counterparts ever touch, they erase one another from existence upon contact, leaving behind nothing but a burst of light. In the first moments of the Big Bang, the universe was a furnace of energy, churning out equal numbers of matter and antimatter pairs. Based on the laws of physics, they should have completely destroyed each other, leaving the cosmos empty of everything but radiation. But a statistical glitch occurred. For every billion matter-antimatter collisions, one single particle of regular matter somehow survived. That tiny leftover fraction is what built every star, planet, and atom we can see today. The man who first realized this mirror world existed was Paul Dirac. He was so introverted, his colleagues at Cambridge joked about a unit of measurement called a Dirac, equal to 1 word per hour. He proved that we can sometimes uncover how the universe is built by following a trail of mathematical symmetry, long before we have the physical tools to see it. By the 1920s, physics was divided. Albert Einstein had already established the rules for the macro world and objects moving at high speeds with his theory of relativity. Meanwhile, Erwin Schrodinger had developed a wave equation to map the behavior of subatomic particles, the foundation of quantum mechanics. But the two systems didn't work together. Schrodinger's equations completely failed whenever a particle started moving close to the speed of light. Relativity and quantum mechanics were essentially speaking two different languages. Other physicists tried to mash the theories together using messy compromises. Their equations were clumsy and predicted negative probabilities, suggesting there was a less than 0% chance of a particle existing. Dirac refused to accept these halfway solutions. He believed that if a theory didn't possess an absolute, flawless mathematical symmetry, it couldn't possibly be true. He found his bridge using 4-dimensional matrices, complex grids of numbers, where the order in which you multiply them actually changes the result. This described an electron in a way that satisfied both Einstein and Schrodinger. And it wasn't just theoretical. The math perfectly explained spin, showing electrons exist in 2 counter-rotating states, spin up and spin down. But there was a consequence hidden in the elegance. The equation demanded that electrons could also exist in states of negative energy. That sounded like nonsense. If an electron could have negative energy, it would continually radiate light and drop into lower and lower negative states, falling forever into an abyss and destroying the stability of all matter. Dirac's fix was radical. He proposed that what we think of as empty space is actually an infinite sea, already completely filled with negative energy electrons. This Dirac Sea is what prevents regular electrons from falling in. There simply isn't any room left. Now, consider what happens if you knock one of those invisible electrons out of the sea. You are left with a hole. Since you've removed a negative charge from a uniform background, that hole would behave like a particle with a positive charge. Dirac had just predicted a mirror image of the electron. The initial reaction was skepticism. Werner Heisenberg was so frustrated by the idea of an invisible sea of particles that he called the theory ridiculous and threatened to leave the field of physics entirely. But 4 years later, a young researcher named Carl Anderson was studying the tracks of cosmic rays in a magnetic field. He captured a track that had the exact mass of an electron, but it curved in the opposite direction. It was a positive electron, the positron. Dirac's hole in the sea was no longer just a mathematical quirk, it was a physical reality. Years later, Richard Feynman provided a cleaner way to look at this, without needing an infinite sea. He showed that these antiparticles are mathematically identical to regular matter, traveling backward in time. Dirac had used pure logic to force the discovery of a mirror image for every particle in the known universe. His work earned him the Nobel Prize and proved that the universe is governed by a deep, underlying mathematical symmetry. It's a symmetry that still holds today. For every atom in your body, there exists the mathematical potential for an anti-atom that could erase it. We only exist because the early universe wasn't perfectly symmetrical. Our entire material world is the result of a 1 in a billion imbalance that allowed matter to win.